It turns out that things that we think of as particles, such as electrons or neutrinos or protons or neutrons, can behave like waves. And things that we think of as waves, such as photons, can behave like particles. This is known as wave-particle duality, and we're still learning a lot about it. Right here, you can see we've got two images here. This first one is a diffraction pattern of X-ray beam, of an X-ray beam passing through aluminum foil. And diffraction is something we've talked about. We talked about the diffraction grating and how it breaks the incoming light up into its spectrum. And what you're seeing here, we've got this diffraction pattern for the X-ray. And, well, this is exactly what is expected. Even though we didn't look at something exactly like this, this is exactly what theory predicts. But then over here, this is the diffraction pattern of an electron beam passing through an aluminum foil. And what you can see is it looks awfully similar. You know, the electron in this situation, this particular setup, is behaving like an X-ray. And that's unexpected. This is what I'm talking about, the wave-particle duality. And a lot of it can be summed up by this formula here. This is the momentum times the wavelength equals Planck's constant. And this works for all particles. It's not just electrons or neutrinos. It also works for photons. Remember, photon is the particle of light. And photons don't have any mass. Doesn't matter. This formula works for all particles. And it says you take the momentum of the particle times its wavelength, you will get Planck's constant. This means that photons, light, which we think of as a wave, has momentum. And this means electrons, which we think of as a particle, has an associated wavelength. And it's all summed up by this nice, simple little formula. There's really nothing more to it. I will say that this idea seems baffling to us, this idea that an electron can be thought of as a wave, because we don't experience that. This is something that really only happens under very special situations. You know, in our macroscopic world, electrons are particles. But there are situations where it can behave like a wave, and that's what we're seeing here, and that's just the idea. And this does have important ramifications.